Welcome back, everyone. In this video I want to continue talking about a couple other types of number systems. I showed this document earlier in the earlier video, and now you should understand a little bit more about it since we went through binary and base 10. So here on the left I have a list of base 10 numbers from 0 to 20. We'll talk about this one today. This is octal, which is base 8. And we'll talk about this one today, hexadecimal or base 16. We've already talked about binary, and the thing here I want to point out is when I want to represent numbers, look at the number of binary digit it takes to represent either a number in any of these other bases. We'll do base 10. So for 0 I can have a 0. For 1 I can represent a decimal 1, and binary just a 1. But when I go to a 2, I got to use 2 bits here. I got a 1 and a 0. I use 2 bits. All the way up to 3. Once I go beyond 3, if I want to represent 4, I got to use 3 bits. All the way up to 7. I go above 7 to 8 takes 4 bits. And you can see what's happening. That as I go to a higher and higher decimal number or any of these other bases, it takes more and more and more bits to represent the same value in another base. So I want to look at that today. What can we do about that? Is there a better way to represent numbers if I have to use a lot of bits and I don't want to have to try to remember a long stream of bits? So let's look at that today and see if there's a solution. Number systems in code. We're going to look at the octal and hexadecimal number systems. Well, as I showed just a second ago, if I express a number in binary, the larger the decimal number, the more bits it's going to take. So eventually you get to the point to where it becomes really difficult to keep track of all those zeros or ones. So to solve this problem, we can use other number systems where we can have just certain symbols represent a large group of bits. And I've already showed those number systems at the beginning of this video. We're going to look at base 8 and we're going to look at base 16. Those are some common number systems used in computer science. We'll look at octal first. Octal or base 8. Base 8 is common in PLCs, PCs, and most digital systems, or I should say many digital systems. The reason is the number 8, if you think about it, we define 8 bits to be a byte, and since a PCs and a lot of digital devices or machines are byte oriented. They don't, the smallest group of bits that it can handle is a byte. It can't go down to the bit level. PLC can actually go down to the bit level, but most digital devices handle bytes of information. So that makes base 8 unnatural for digital devices. Go back to this formula we talked about before, that the base tells us the number of symbols. So base 8 means we have 8 symbols. If I take the base minus 1, it tells us the value of the highest symbol in that particular number system. So a base 8 system, I can go 0 through 7. I can use symbols digits 0 through 7. There is no 8 and there is no 9. This table is simple but important. So what we're going to do is, when we think of octal and compare it to binary, we'll use 3 binary bits to represent the octal numbers 0 through 7. So it only takes 3 bits to represent all of these. 7 kind of sets the tone for us, because to get a 7, once I go beyond 7, I need a 4th bit. So I can handle 0 through 7 and only use 3 bits. So in octal, when we want to represent octal numbers in binary, there's a 1 to 3 relationship. One octal symbol, I use 3 binary symbols to represent it. So you want to remember that. Now here's that position weighting we talked about in a previous lecture. So once we know the base, if I start counting this position, if I start with a 0 instead of a 1, I go 0, 1, 2. Then what happens is that position that I'm counting, it becomes the base raised to the power of the position, and that'll give me the weight for each of these. So in any base, this will work. Last time we talked about this, we used base 2. This was 2 to the 0, 2 to the first, 2 to the second, 2 to the third, and so forth. Well, in base 8, I do exactly the same thing. This is 8 to the 0. This is 8 to the first. This is 8 to the second. So that gives me a weight here, a weight of 1 here. I have a weight of 8 and 64. That's a 1, that's a 8, that's a 64, and I can keep going if I wanted to, 8 to the third, fourth, and so forth. But let's say I have a octal number. I have the octal number 462. Now, I know it's octal because I'm saying here's an octal number, but if this were written on a piece of paper or on a whiteboard or blackboard, how do you know that's not 462 in decimal? Well, the way you would show that is with this little subscript of an 8 there. So once you start dealing with these different number systems, it's very, very important that you must subscript. As a matter of fact, if you don't subscript and you turn in work and it's unsubscripted, you'll lose points. So please, please, please use subscripts. But the point is here that I can easily get the weights for each position here. And I see that I have a 64, a 8, and a 1. So if I take the weight times the value, I have a value of 4 times 64. I have a value of 6 times 8. I have a value of 2, and that value times 1. So I can do the math here. 64 times 4, 256. I can take 6 times 8, 48. I can take 2 times 1 is a 2. I add those up, and what I get is 310. So what does that mean? What it means is 462 in base 8 in our number system is 306. So you can easily convert from octal to decimal using this position weighting method here. And so make sure you practice that and you know how to do it. I'll ask about this at some point on the test or quiz. It's pretty simple. And once you get the idea here, hopefully you can see from base 10 or the base 2 discussion we had before, that once you understand one number system and you kind of understand number systems in general, then any number system you can do, and it's all pretty easy. It's all the same. You just got to watch for the number of symbols and the value of the highest symbol, and then get these weights right, and then you're good to go. What if you want to go the other way? What if you want to convert an octal number to binary? Remember, and I want to stress this, someone actually asked this question in the live stream. It was a really, really good question, but I want to make sure you're clear. We are talking about different number systems. We talked about base 10. We're talking about base 8 now. We're going to talk about base 16. But remember, no matter what base we're talking about, the only thing that goes into a computer is base 2. So no matter what number system we are talking about, it's very important. No matter what number system we're talking about, what kind of code we're talking about, everything goes into the CPU as zeros or ones. Everything gets converted to binary. It could be a binary number or a binary code. We talked about the difference between a code and the number, but everything gets stored as zeros or ones. So there is no octal inside of the computer. There is no hexadecimal. There is no decimal. The only thing that exists inside of a digital device or machine is binary. So anything other than that, if I'm trying to put an octal number into a machine, I got to do some kind of conversion. I got to convert it to binary, which is what we're doing here. So to go to octal, from octal to binary, is really, really, really simple. All you got to do is every octal number, write that out in binary as 3 bits. So 4, I'm going to write that using 3 bits as a 1, 0, 0. 6, I'm going to write that using 3 bits as a 1, 1, 0. 2, I'm going to write that using 3 bits as a 0, 1, 0. And then I just put all those bits together, and there we go. I got it. So there is the octal representation. Here's a representation of that octal number in binary. Now, if I was going to go the other way, let's say I gave you, not go the other way, but let's say I gave you, if I gave you this number on the bottom, if I gave you that, you can just divide this up into threes, and you can convert that. You can convert that back to an octal number pretty easily. But sometimes students will get confused, because if I don't give you, like here you have 9 bits, right? You have 9 bits here. So it's easy to divide. I got 3 and 3 and 3. Well, if I gave you only 8 bits, what you'd have to do is, let's say I gave you 3 here, and only 2 bits here. Maybe this was a 1 and a 0. What you would do is put a 0 in front there. You would just add that other bit, because you got to have groups of 3s. So if you don't have a number of bits that's divisible by 3, don't get confused. Just add leading zeros, and you'll have groups of 3s, and then you can remember this slide. So this is probably for the octal. Mark this slide, and I know you guys are taking notes. This is a good slide to remember. So octal is pretty simple. Base 16 is just as simple. So I want to talk about base 16. Now there is one little difference here. So for base 16 means I'm going to have 16 symbols, and the value of the highest symbol will be the base minus 1. Well, 16 minus 1 is 15. So I can use the symbols 0 through 15. But notice this. If I go from 0, I don't know if I said 0 through 16, 0 through 15 is what I meant to say. But look at this. If I go from 0 all the way up to 15, once I get right here in decimal, once I get right there, I run out of symbols, because decimal is only good for 0 through 9. There's 10 symbols, 0 through 9. So once I run out of symbols, I got to start repeating. Well, I don't want to have to do that over here. I want a one-to-one relationship between a symbol and its decimal equivalent. So that's okay over here. It works from 0 up to 9. Yeah, there's a one-to-one relationship between hex and decimal from 0 up to 9. They're the same. But once I go beyond 9 over here, where I have to start to repeat, I don't want to have to do that in this new number system. I want to have one symbol represent that decimal value. So what we do is, so that we can have 16 symbols, 0 through 9. Well, that's 10 of them. So I got to get some other symbols here, because I ran out. I've already used 0 through 9. I used those 10. I gotta get some more here. So what I do is we use letters of the alphabet to represent symbols. So what you remember is A has a decimal equivalent of 10, B 11, all the way down through F is 15. So if you can remember that A through F is equivalent to a decimal 10 through 15, A is 10, B 11, C 12, D 13, E 14, and F is 15. If you can remember that, then this is a piece of cake. You'll see how easy this is. So let's look at an example. Using my position weighting, this is base 16. So this will be 16 to the 0, 16 to the first, 16 to the second, just like in all the other number systems we've done. And so my weights here would be a 1, a 16, and a 256. Now, let's say I give you this number, and I want to convert this number, and I should have a 16 here. It's clear from this that this is base 16, because that's what this is about. But technically, you want to subscript a little 16 here. But if I give you a 1B7 in hexadecimal, or hex for short, how would I convert that to decimal? What is that in our number system? Well, this has a weight of 256. I got one of those, so I have 1 times 256, which is 256. I got B of those. Now B, if you remember from this slide, look at B. B has a value of 11. So B is equivalent to 11. So when I do my multiplication, B is really in your mind, think about 11. So here I got 11 times 16, which is 176. And then here my unit column, I have 7 times 1, which is 7. So if I add those up, what I'll get is 439. So a 1B7 base 16 is 439 base 10. In our world, this is what it is. If I want to go from hex to binary, now remember when you went from octal to binary, what we did is we just wrote each octal number using 3 bits. But we do the same exact thing here, only we're going to write each hex symbol using 4 binary bits. So if you can remember that, then this will be really easy. This I'm going to write in binary using 4 bits. This value I'm going to write using 4 bits, and this value I'm going to write using 4 bits. So if I write 1 using 4 bits, I get 0, 0, 0, 1 in binary. Now B, now remember that's 11. B is 11. So if I write 11, this right here using my 8421 code, this would be an 8, this would be a 2, which is 10, and this would be a 1, which is 11. So I would write a 1, 0, 1, 1, again using 4 bits, and I write 7 using 4 bits. Put all those bits together, and then what you have is a 1B7 base 16 is equal to all these bits right here in base 2. So this is actually pretty easy. Once you get this and understand number systems in general, then it's a piece of cake. So I don't foresee you guys having any issues with this stuff at all. But if for some reason you do, you need me to re-explain something, or you just have general questions, please send me a text or email, and we'll get that taken care of. So you guys have a great rest of the day, and I'm going to do one more video for today, and we'll end this week's, which dealt with number system. We'll end this week's lecture with one more short video. So guys, have a great one. I'll see you in a second.